Hello, today I'm going to be presenting domain generalization by rejecting extreme augmentation. This is a joint work with Fidel Peña, Heitor Rapela, Dubail, Granger, Marco Pedersoli from Libya DTS. So first, I'm going to go through motivation and then define the problem and then our contribution and finally our method and results. So the goal of this paper is to tackle domain generalization, and the definition of domain generalization is usually we are provided with several different but related domains during training, and we are trying to use them and generalize well and unseen test domains. So, so far, the observation that we have in the literature is that simple ERM, meaning that we pull all of the training data into one big data set, and then randomly sample from it and apply a strong data augmentation, has a strong performance compared to a state-of-the-art for OOD generalization. One intuition on why this could be the strong case is like as data augmentation getting stronger or wider, it covers the space of more possible images, and but there's a kind of a catch that sometimes these data augmentation can destroy the semantic content of the image as well. So first we test this idea, like if we make the data augmentation even more stronger, how much we can gain from it. So we started from ERM baseline using the big search space that has been defined in the domain bed, and we tried different data augmentation strategy, and we came up with our own search space, which is based on the TA search space, but we made it wider. And as we can see here, as the data augmentation is getting more stronger or wider, the average performance is getting better as well. So this is one empirical proof that indeed strong data augmentation is helpful for DG. But the problem is, like, as data augmentation is getting stronger, the possibility of destroying semantic content of the image is more likely. So is there any workaround around this? So this is one example to show that, for example, for translate X, there is a possibility that we destroy the whole images, and we want to avoid having these images during training. So our contributions, like first, we show that the expansion of the transformation increased the performance. And then we came up with a new schema to find a good trade-off between these expansion and the optimal one. And then we show that our method has really a strong performance on 5 benchmark from domain generalization setting. So basically, our method works by rejecting extreme augmentation. So here in this picture, we can see the two samples from our method. So first, we start from a base image X. First, we augment it with transformation week, and then on top of transformation week, we sample from transformation wide and augmented one extra step, and then feed both of these to our method. And then during training, our method has a chance to decide which one to use. And we propose a reward function to find the best trade-off between these two. Here in these two examples, we can see that our method find the weak one the best for the end classifier, and in the other example, our method finds the wider better than the weak, because wider actually is more diverse. So our reward function is based on student-teacher schema, and the reason behind that is like we use a student as an agile and diverse model, and use teacher as a consistent and lazy model. So teacher help us to decide robustly, and a student help us to decide diversely. So we designed 2 different reward functions based on two different information that we have. And one extra information that we have usually in DG is the domain metadata. So we have one based on domain info, and if we don't have any information from domain info, we can use just label, and we have reward for both of them. So specifically for the case of domain info, we defined our reward for diversity based on the loss of domain classifier, and we try to maximize this loss, and simultaneously use the EMA version of the teacher to maximize the consistency as well, which is the negative of this reward. And then combine both of them as our final reward function. So in a way, we try to have the most diverse and most consistent image, and then based on that, we select one of these for the backward pass. And the same thing goes for the label, but here we only replace domain classifier with label classifier. Here we have a catch in label info that we can deploy the teacher version of the classifier, which is most usually the more robust version, as a final product. So here in the table, we compare our method with different baselines, and as we can see, all of our proposed method is better than the rest. But we can just increase the gap by 2% if we use the teacher version of the classifier, which is usually, as I said, more robust. Here we also show that our method not only give us the good OOD performance, but since we are kind of compromising or trading off in the search space of data augmentation, we can also have a really good result on IID. So here we kind of ran the same experiment, but instead of just showing the OOD result, we just show the result on the validation, which is in domain. And we can see as data augmentation is getting stronger, usually the IID result is getting worse, exactly the opposite of the in domain. But our method find a good compromise between these two and give us the really good IID result as well. And finally, we try to quantify the search space that we came up with. So usually we use two kind of metrics. The first metric is affinity, which calculates how much we change validation data set after augmentation. And the good data augmentation should be consistent, meaning that validation after data augmentation should follow the same validation before data augmentation. But diversity needs to measure how much the training, actually, the actual training become harder as we augment the data augmentation, because it shows that like the data augmentation has actually become more strong. So in this graph, on the y-axis, we can see the diversity, and on the x-axis, we can see the consistency, and the color of each method shows the final performance. And we can see that our method has a good trade-off between diversity and consistency. On both ends, here is our TA wider, which kind of like shows the most diverse but least consistent. And here the baseline VRM, which is the most consistent but least diverse. And in both our case, we have a good trade-off between both of them. As a conclusion, for next step, we try to incorporate broader range of transformation into our pipeline, and also extend this work to different tasks like detection and segmentation. And thank you for your attention.